Next speaker today is Everett Patterson. He's a student at the University of Waterloo, and he's going to talk about probing BTZ black holes via fission information. Everett, whenever you want, the floor is yours.
Fantastic, thank you. So yeah, I have an archive paper with a similar, albeit slightly different title. The link is here and I'll post it in the Slack as well. But the work that I'll be sharing today is, as the title suggests, using Fisher information to glean some sort of better understanding of the BTZ black hole. So the motivation for this work stems from previous work done within my group. So Dr. Mann and Haoxing Du did some sort of Fisher information analysis of four-dimensional de Sitter and anti-de Sitter spacetimes. And we wanted to build on that and consider what happens if we bring that to a black hole spacetime. We know that black holes exhibit different behavior from asymptotically curved or flat spacetime. And we wanted to know how that might translate or percolate through in the case of Fisher information. So Fisher information has some value in improving measurement procedures when it comes to relativistic quantum metrology. And I was also curious to know whether we might be able to use this Fisher information as a discriminant of the spacetime. Looking only at it, would we be able to distinguish between spacetimes? So to look at a black hole spacetime, we've considered the BTZ spacetime in 3 dimensions, in part because it can be obtained using an image sum from ADS, 3-dimensional anti-de Sitter space, which will also allow us to compare to the previous results in the literature. That analysis did not make it into this talk, but there are extra slides, and I'll try to share my slides in Slack as well for those of you who are curious, and there's some comments in the archive paper as well. So relativistic quantum metrology is kind of the branch of RQI under which this research falls. It's the study of making a measurement, or more often parameter estimations, of a quantum system accounting for relativistic effects. This parameter estimation is, the primary methodology used within the field, and it's when we try to understand measure essentially some underlying parameter by looking at the value of an observable parameter when the underlying parameter is not available. And we quantify this using Fisher information. So here we have a definition of the Fisher information where the probability P of measuring X, in our case, it's going to be the state of our detector, either excited or in a ground state. And then the underlying parameter psi, in our case, this will be the temperature experienced by the detector, where our detector is going to be an Unruh-DeWitt detector with the interaction Hamiltonian coupling it to a massless scalar field. Our detector has an energy gap omega, and this energy gap will become especially relevant with the response rate below boxed in red, in that the energy gap is always found in this fraction with the temperature. So it appears here, and then it appears in the complex indices of these Legendre polynomials. So this is the response rate for the BTZ spacetime, and this, using an open quantum systems paradigm, is really the core function. All the results kind of depend on this function. And we notice various variables. So there's this energy gap, there's this temperature. We have the mass of our BTZ black hole. And there's also this n, which is the index for the sum, which allows us to take our ADS, either response rate or Whiteman function, which are related to the BTZ spacetime. In particular, when n is equal to 0, we're going to recover the ADS results. You can see the mass term doesn't come into play when n is equal to 0. And in the alpha minus parameter here, we're going to get just the 1 left over, and this Legendre polynomial term will be 1, and we get a much simpler model. So comparing ADS to BTZ, here we have across the columns, we have theta, which is the initial state of the detector, which I kind of glanced over or actually skipped outright in this talk. We're not going to worry about that too much. What I really want to draw your attention to are the rows, which are defined by the energy gap and the temperature. We have our solid lines are the ADS spacetimes, and the dashed lines represent the BTZ spacetimes with Fisher information on the y-axis, which will be consistent throughout the talk. And for most of the talk, we're going to have time along the x-axis. And what I'll draw your attention to here when we're comparing ADS to BTZ is the fact that when the energy gap is equal to the temperature, we see no difference between the Fisher information of the ADS spacetime and the BTZ spacetime. So this first and fourth row have omega equal to t, while the second and third row, when t is greater than omega, we kind of dub this the hot case. And when t is less than omega, we dub this the cold case. And in those two cases, we notice there is a discrepancy, there is a difference between the BTZ Fisher information and the ADS Fisher information. And in particular, the discrepancy in the transparent boundary condition in black in this cold setup does allow us to discriminate between the spacetimes. This is a qualitative behavior that is not present in ADS, but is present in the BTZ spacetime. But for all of this, we've set the mass equal to 1 to best compare ADS and the BTZ spacetime, not trying to not account for what happens from mass variability. But if we're considering a black hole, we want to consider what happens, what is the dependence of the Fisher information on the mass. And so doing this, we're gonna color code using the colors of the rainbow. So red corresponds to a small mass of 0.01, and purple corresponds to a larger mass of 1.5. And we see when the energy gap is equal to the temperature, a rather smooth evolution of the maximal Fisher information, which is when you'd want to measure your detector to gain information about the underlying temperature. We see it's really quite smooth. In the Dirichlet boundary condition, which I now realize I forgot to point out in the response rate, but it takes values of 0, -1, and 1, and it is present in that formula. We notice a slight increase when we're going between the yellow and green curves, so a mass of 0.1 to 0.5. There's a slight increase, but essentially a very smooth behavior. And that's rather different from the case where omega is not equal to t. In this case, we've presented the cold case. There is some variation depending on the initial state of our detector, but there's also some variation once we've established the initial state and the boundary conditions. So we're going to zoom into this first plot. And if we follow the colors, we go, red, orange, yellow. Okay, we're shifting and then we're decreasing, but it's rather smooth. But then once again, when we go from a mass of 0.1 to 0.5, we go from yellow to green, and we're kind of backtracking. So we have this kind of oscillation. We go back down to the mass of 1 and then back up to the purple line. And it's not obvious why this comes about. We're not entirely sure. We don't have a great analytic understanding of this, especially because the mass term in the response rate comes in through Legendre polynomial with complex subindices. But we figured, we can do better. We can learn a little bit more, try to better characterize this instead of just saying, it's hopping all over the place. So to zoom in on it, we're considering here a mass still from red to purple from 0.01 to 0.13. And we notice now it's smooth again. So for this small mass regime, we have a smooth evolution, which, okay, that's cool. And then if we consider the next set of masses from 0.15 to 0.5, we start with this red, which is almost not present. Almost not present in this graph. And then it goes up to orange, yellow, and it jumps up to green for a mass of 0.3 before dropping back down dramatically for the mass of 0.4 and then back up for the mass of 0.5. So obviously something interesting is happening for this mass regime. Once again, not entirely evident analytically why this is happening, but if we have a black hole with a mass of 0.3, we're gonna get a much better estimation of the thermal parameter because we have a much higher Fisher information. Now, to make a more direct comparison, let's fix time. In this case, we've set tau, the proper time of the detector, to 10. And we're comparing when the energy gap is equal to the temperature versus when the energy gap is greater than the temperature. And we see when they're equal, we have a slight monotonic decrease in the Fisher information, but relatively constant overall. As opposed to in the cold setup, we have these rather dramatic oscillations where we get really large Fisher informations, which would be great for a measurement procedure if the mass of our black hole is here, but shifted over slightly and we get a really poor estimation with zero Fisher information. So there are some instances where we should maybe tune our detector if all else is equal and we get to choose the energy gap of our system. There are some instances where we're going to want a greater energy gap or a different energy gap from the temperature. And other instances, for example, if we have a mass around here, we're better off to actually tune them more similarly. So that is my talk. I will, share these slides and post a link to the archive in the Slack. Thank you very much.
Thank you very much, Everett.
So, very nice talk. I think I blinked and missed, what is the trajectory of the detector?
Yeah, sorry. So in ADS, we have a constantly accelerating detector. And in the BTZ spacetime, we have it stationary.
Stationary in the BTZ coordinates?
Yes.
Okay.